Uh, Great. So we got the recording going. Welcome everyone to the Purdue Topology Seminar. We have Benjamin Haïoun. He's going to tell us about handle attachments in TQFTs. Thanks, Ben.
Okay, thanks for the introduction and for the invitation. Yeah, thanks everyone for joining. Um, so today I would like to talk a bit about TQFTs, which many of you might be familiar with, but I will recall my take on it anyways. And handle attachments and somehow how these two things play together. Uh, um, yeah, I think the talk is rather short, so there's time for plenty of questions. So if anything I say is not fully clear, then feel free to interrupt, and I'm very happy to make extra drawings for you. Um, okay, so let me start with TQFTs. So this stands for Topological Quantum Field Theory. And so it is a mathematical notion, but it's supposed to model something physical. So the idea here is that we're a kind of physical theory. So this kind of quantum field theory, what it will do is that from a space M, which is real space we live in, maybe, it will assign to me a vector space Z of M of all the physical states on M. So one way you can think about it is like, for example, classical mechanics will give me some phase space that tells me all the positions and speed of all the particles I'm looking at in my system. And so that's kind of the thing that describes a point in there describes as a physical state of my system. So now that's not a vector space, but if you're doing quantum, then maybe you want some wave function in this form of vector space. And what's also particular with quantum field theory is now it's not actual particles, but some fields that I don't need to specify to you a number of and types of particles living in M. It's really, I'm just giving you the space in which things live, and you have a well-defined vector space that will encode all the ways there could be particle living in them. And this forms a vector space. Okay, so that's for this part. And then if I have a space-time, which I will think of as manifold one dimension higher that kind of joins two spaces, M and M prime, then I would expect my physical theory to kind of give me a way, a time evolution along this space-time. So this will be just a linear map from my first vector space to my second vector space. So if you give me a state in M and I want to ask, okay, what happens after time W, then you need to give me a state in M prime. Okay, oh, here's how it evolved. Okay, cool. And topological here means that this time evolution operator really only depends on the topology of W. So it's depends on W up to diffeomorphism. So I don't need to give you a metric on W or anything like that. This might be a little surprising from a physical perspective. In general, theory from physics, you don't expect to be topological, but there are some examples that happen to be, and also they are the only examples we really know how to formalize in math, so it's still quite interesting to look at. Okay, so for me now, let me give a proper definition. So a TQFT in some dimension n, here's the dimension of spacetime, is a symmetric monoidal functor from some category of cobordism to some category of vector spaces. So the category of cobordism, it has objects n-1 manifolds, so that's my space M, closed, oriented, and smooth. I won't repeat these words again, but they're always true. Maybe not closed. Um, And the morphism from space M minus to a space M plus will be an cobordism, so an n-dimensional manifold with boundary decomposed into an incoming path and the outgoing path. Okay, and vector spaces is vector spaces in linear mesh. So really this functor is encoding exactly what I told you before. To space and n-1 manifold, you assign a vector space into a cobordism between them, you assign a linear map, and this should preserve composition, and also it should send disjoint union to tensor product. Okay, so I've have my mathematical definition for these topological quantum field theories. And now this is quite interesting, even if I forget all the physics about it. For example, out of this, I get an invariant of closed n manifold. Okay, a closed N manifold I can think of as a cobordism going from the empty N-1 manifold to the empty. Okay, and the empty is the monoidal unit for disjunct union, so it will be mapped to the one-dimensional vector space, the field K. And so my TQFTZ on this closed N manifold, it will give me a linear map from K to K, and this is just a scalar. So I get a scalar, a diffeomorphism invariant of closed N manifolds. This is always nice. It can help me distinguish N manifolds, maybe. Moreover, it's really computable. So if I manage to cut my N manifold into two pieces, okay, say W1 and W2, then I should have a recipe. Somehow the fact this is a functor tells me I can compute this invariant as a composition of two linear maps, Z of W1 and Z of W2. So kind of this invariant is very computable if I cut things. Okay. Any questions so far? Okay. So we'll be interested in TQFTs that are actually even a bit nicer. I can cut a little bit more, so which we call extended TQFTs. So for example, if here I'm looking at a torus in dimension 2, for a usual TQFT, I can chop this up into these four pieces. Okay, and then somehow I cannot cut it any smaller. These will kind of be the elementary blocks for my 2D theory. In an extended series, I can chop this even further, and I can also cut in another direction. Okay, so here I can only cut in this direction, and in an extended series, I can cut in more directions. Okay, and so this will allow me to, well, in this case, decompose this torus into even smaller pieces. Okay, so maybe for surfaces, it's not clear it's that interesting because I mean, okay, this was not that complicated anyway. But in higher dimensions, it really changes something that I can cut even further. Um, so okay, so now I have this extended TQFT that gives me some linear maps assigned to cobordisms and that behave very, very well with cutting and pasting. Okay, so I want to define to you what is an extended TQFT, again, a bit more formally. And so here, kind of what you're looking at here is some kind of cobordism with corners. Okay, I really see these corners here. When I cut something twice, I'm just introducing a corner quite naturally. So, okay, first, what is a cobordism with corner? So it is so yeah, I've changed my mind about the space-time dimension. Now it's n+2 because I have 3 dimension involved and I'm too annoyed of being n-1, n-2, n-1, and n. So it's n+1 and n+2. So W is of dimension n+2. And so somehow it's good to have a picture in mind. It will have two kind of boundaries. One is the incoming and outgoing boundary. So these are two n+1 cobordism, m plus and m minus. Okay, so here I have m minus. M minus itself is a cobordism from sigma minus to sigma plus. And m plus is another cobordism from sigma minus to sigma plus. Okay, so here I have a cobordism m minus, and here I have another one. Okay. And so if you give me these two cobordism, m minus and m plus, then I can talk about cobordism with corners between m minus and m plus. So something filling this thing. And its boundary will be, well, m minus and m plus, okay? And also something that I will call the side boundary, which is secant. So sigma plus and sigma minus is a boundary of m plus and m minus. And I take this times the integral. So maybe it's, I mean, a long list of equations was a bit too annoying, so I thought a drawing is maybe the best way of doing this. So it's really the picture you want to have in mind is, okay, before my two boundaries, m minus and m plus, were closed. Now they are not closed anymore. They may have boundary, and this is the red part, okay? And somehow W preserves this boundary very well, and this boundary is just unaffected throughout W, okay? So this will kind of think of uh, a way of transforming a manifold with boundary M minus into another manifold with boundary M plus. Okay, that doesn't affect the boundary. Okay, and so these cobordism with corners, they assemble into a two categories. So now I have objects are my corners, my closed N manifolds. One morphisms are just cobordisms as before. So this is my M plus, and M minus are just N plus one dimensional cobordisms. And then two morphisms are these cobordism with corners, kind of filling this picture. Okay, I have M plus and M minus on either side, sigma plus and sigma minus on the top and bottom, and I have something filling this picture. So kind of in two category picture, this thing, my objects, I will kind of stick with red for the corners. Um, are my objects are my corners. My one morphisms are just cobordisms, and then I have something filling this hole.
So Ben, I'm curious, at some point, usually someone says, often people say up to diffeomorphism at some level.
You're right.
So
Yeah, I should have.
so it's that only the top dimensional things are considered up to diffeomorphism.
Yeah, only the last one. That's a good point. Yeah. Um, there's some more subtleties that I don't want to dive into about giving colors to the boundary. Um, but yeah, maybe
Okay.
this
Yep.
part was that's a good point. Um, okay, and so this list of things, it has some good structure. So it's a bicategory. So what this means is that there's two kind of operations I can do, and they're kind of displayed over there. If I have a cobordism from M minus to M plus, and then another from M plus to M something else, then I can just glue them together and obtain just one cobordism with corners from the first to the last. Okay, so this is composition of two morphisms in the usual direction. And I also have another kind of composition of two morphisms in the other direction. So if I have something from, say, here empty to sigma minus and then to sigma plus, I can compose these two things and get something from the empty to sigma plus. So there's two directions in which I can glue these cobordism with corners, either along the boundaries M plus and M minus, or along the corners themselves. Okay, and so these two directions is really saying this is a two category. And the structure is really what I'm going to use and to talk about handle attachments. Okay, so maybe let me just include the definition of 1/6 standard TQFT is, as before, an assignment from these cobordism into some target category. I don't want to give in detail, but it's something linear. It's something like vector spaces, but now it's a bi-category, a two category instead of being a one category. Okay, so what we want to look at is some functors out of that. So some thing that will give me something that looks like a linear map to cobordism with color. Okay, um, and so the result I want to build towards is this presentation of this category. So, okay, this is a category I'm interested in, and I'm gonna try to present it as an extension of a smaller category where I've adjoined some morphisms cushioned by some relations. Okay, so this kind of category I'm starting with is very similar. So it has the same objects. My objects are still n manifolds, the same one morphisms, still n plus one cobordisms, but instead of having any kind of n plus two cobordism with corner, I will only look at diffeomorphisms of n plus one cobordisms. Okay, this is a special case of a cobordism. We'll see this in an instant. But somehow here there's nothing of dimension n plus two. Okay, so I've gotten rid of everything of dimension n plus two, and I'm just looking at somehow everything of dimension n plus one at most in there. Okay. And so the only things of dimension n plus two I'm going to allow is these handle attachments. So this is a very particular n+2 cobordisms that I will define again in the next slide. But so there is a finite list of people I need to add, and if I just add these things of dimension n+2 and allow anything of dimension n+1, then I can generate the whole category. And moreover, the relations are again very well understood, and it's just Hadot constellations. So I will also say a word of what these are. Okay, so I have this great presentation of the cobordism bicategory. You may wonder what it means to present two category with generators and relations. And so for us, what this means is it describes what is a functor out of this thing. Okay, so a functor out of this thing, so from this to C. So once extended TQFT is the same thing as a functor out of this thing and an assignment for each of these generators satisfying these relations. Okay, what you would expect from a presentation. Okay, so my once extended TQFTs now, they are completely classified by something only defined in dimension n+1 and just finite number of two morphisms for each of these generators, satisfying some relations. Okay, so somehow this will be, I mean, this is very useful for me doing quantum topology to like actually define some TQFTs. Okay, so how this is a good motivation for you too. But this is what I want to build towards is really understanding, reducing everything to dimension n+1 and just these generators. Okay, this is also, I mean, if you know some Morse theories, this is probably very unsurprising. Everything is generated by Handel attachments. So somehow the proof is really Morse theory and some two-category theory. But we'll see that somehow the two play really nice together and make the statement much simpler than what you would expect at first sight. So maybe we'll have time to go back to this a bit later. Okay. So first, Handel. So what are these generators? So the Handel attachment HK, so it's going to be a two morphism in my category, so an n+2 manifold with corners. The corners are going to be some product of spheres, so sk minus 1 across Sn+1 minus k. The incoming n+1 cobordism is this sk minus 1 cross a disk, and the outgoing is a disk cross a sphere. Okay, so somehow what you should have in mind here is that somehow my hk looks like dk cross d, what is it, n+2 minus k, a product of two disks. And this product of two disks has two boundaries. One is the boundary of this one cross this disk, and the other one is this disk cross the boundary of this one. Okay, and these are these two things. The problem with the product of two disks is that it's not really cobordism with corners in the sense I said before. I wanted the corners to be, a sphere cross an interval, to be sigma cross an interval. In the product of two disks, it's not really this type. So the way, a slightly nicer way to describe this handle is to think of the Morse function that defines handle attachments typically. So I have a Morse function in n+2 variables. Okay, my dimension s+2, n+2, and so it's a sum of square with k of them having a minus sign and the rest having a plus sign. Okay, and so in dimension 2, for example, here k equals 1, okay, you will have a k of them kind of going down and n plus k of them kind of going up. N minus k. I mean, n plus 2 minus k. Okay, so I'm drawing a sphere because it's the only dimension I can draw, but you can imagine it's some kind of a saddle, sorry, but it's some kind of generalized saddle with some paths going up, some paths going down. It's drawing me a picture like this. And this we want to think of as a cobordism going from the preimage of -1 to the preimage of +1. Okay, so it's kind of drawing my cobordism. My function is really drawing my cobordism, and I can see kind of the top part and the bottom part just from my Morse function. Okay, so it's kind of the usual thing with Morse functions is each level set, so f inverse of some fixed value. Um, Somehow, if you're away from a critical point, when you change this value, it doesn't really change the manifold, which is kind of what you're saying here. These gray lines, they are level sets of my manifold, and just when you reach a critical point, which is the saddle point here, um, these level sets will change. Something will happen, and what exactly happens is exactly the head. Okay. So again, I've drawn some examples here in dimension. So n plus 2 equals 2, total dimension 2. The 0 handle is a half sphere. The 2 handle is the other half sphere, and the 1 handle is this saddle. Okay, is everyone happy with handles? Cool. Um, Okay, so now I have these two morphisms, and I want to talk about handle decomposition. So I want to say in what sense the handles generate my two category. So instead of just having an abstract handle, I want to have a handle on a fixed n plus one manifold. So this is dimension n plus one. Okay. So in order to do this, all I need to do is to embed k minus one sphere across some disks, so a secant sphere, into my manifold. And then from this, you can do your usual surgery or handle on your manifold. Like you will remove the image of this and replace it with something that has the same boundary but is different. The something is dk cross a disk cross a sphere. It changes what's inside of this. Okay, so the way we implement this in this two category is having this embedding. I can think of M as having kind of is being split into two parts. First, I have the image of the thing, which is just a sphere across a disk, and then I have the exterior. Okay, everything else is also a cobordism, uh, but now has an extra boundary component, which is this sk minus one cross sn plus one minus. Okay, so I have this that embeds in my n plus one manifold, and I just kind of think this as a decomposition of the manifold M, okay, into a composition or gluing of two things. Okay, and now I just recognize this thing, and on in here I can do my handle attachment, and so this is really the informal thing I was saying just before. You've removed the image of S and replaced it with this thing. Okay, now you have a new composition. Okay, so somehow this whole thing, it is a two-morphism in my category that is obtained as a composition in various directions. Okay, you've used both this direction and this direction. Well, here I use a diffeomorphism and essentially a handle attachment. Okay, so this is really the kind of picture that will show up. So maybe I can just mention that indeed a diffeomorphism of n plus one manifold induces cobordism with corner. Okay, so if my diffeomorphism is phi, I can just take M cross an interval and use the identity to identify with M on the bottom and phi to identify it with M prime on the top. Okay, so great. I have these two kinds of cobordisms. These that I called W of S, where S is the embedding of my secant sphere, and these that I call W phi, where phi is the diffeomorphism. So both of these things are either of dimension n plus one or essentially just one handle and glued, composed with many other things that are very simple. Okay. So yeah, maybe one example of this. So again, I'm in n plus 2 equals 2, so I can do drawings. And so I'm going to embed um, two intervals. So this is S0 cross D1, so k equals 1, into, well, the one manifold I've chosen is this circle cross an union an interval. And well, there are many ways I could embed two intervals in there. But for example, I could put them on two different connected components. And then my cobordism, what it will do is kind of do a one handle that attaches on here, and so glue these two things together. Oops. Or I could embed them both in the same connected component, in which case I will have something that kind of splits this connected component into two parts. Okay. But I just gave you this example to emphasize that no, both of these operations of merging two connected components and splitting two connected components, they're both realized by the same morphism, this one handle. Whereas if you were not allowed to cut as much, if you only had, say, a non-extended TQFT, then somehow these are two different things, right? The two pairs of pens that split a circle and that merge two circles, the differences are not related in any, you cannot obtain one from the other in any of this way. Okay, so this is just to emphasize that somehow allowing myself to glue even with these identities and diffeomorphisms on the side everywhere, it's kind of giving me a lot of freedom. Okay, and so handle decomposition now is a decomposition of my cobordism as a composition in my category of many pieces, all of which are either handle attachments or diffeomorphisms, mapping cylinders of diffeomorphisms. Okay, and so great. What I want to look at now is, well, okay, first state that these things exist and also study how unique they are and what kind of relations can relate to such decompositions. Okay, so maybe before I go on, is there any questions so far? Okay. Um, okay, so yeah, this I said you have this kind of there's rather recent, I mean, few years old paper of UHAS that does a very similar result, where he shows that these handle decomposition exist and are unique up to a series of relations. Um, so the first is that somehow the relations you would expect. This is maybe the theorem you would expect from Morse theory is, okay, handle decomposition exists. We know that any cobordism can be decomposed into a bunch of handles. And the relation between these handles that you may know is that, well, these 10 handles commute. So if two handles are glued on different parts of your cobordism, of your n+1 manifold, you can attach one first or the other one first. It doesn't really matter. Diffeomorphisms and handle commute in a weird way. So if you have a handle and then a diffeomorphism, you could have a diffeomorphism and then a handle. Just you kind of move your handle through the diffeomorphism in an appropriate way. But so you do have a kind of commutation like this. And both of these relations, they are a bit unpleasant because they kind of depend on the ambient manifold you're working in. Okay, you have kind of, I don't know, the first one, you have one for every way of putting two handles in an n+1 manifold. There isn't the commutation of the K handle with the L handle, there's just one relation between these two things. So it's so if in the theorem of Juhas, in the natural way of writing this, this is an infinite number of relations between the handles. Okay, and then there's another kind of relation that's the handle cancellation, and this is a finite number of. Okay, so the K handle cancels with the K+1 handle. So if you've never seen this, maybe the nicest picture to have in mind is this thing where here I have drawn a one handle. In dimension 2, here I've drawn two handle, and if you do one after the other in the correct way, then they just cancel each other and you have done nothing. Okay, and so in general, you kind of have think I had this over there. You have an attaching sphere for each handle and a kind of belt sphere, just attaching sphere if you read it in the other way. Um, so in the incoming part you have the attaching sphere, in the outgoing part you have the belt sphere. And if the attaching sphere of the K handle intersects the belt sphere of the K plus one handle exactly once and transversely, then they will cancel. So, okay, this is just saying there is a cancellation of the K and K plus one handle, and there's exactly one of them. There's one composition of these morphisms that is equal to another thing. This is just exactly this relation. So this is a finite number of relations. Okay, there's another one that I will kind of sweep under the rug because it happens that we can sweep it under the rug. But somehow you can reverse how you attach your handle that doesn't affect your handle. Okay. And so kind of the interesting point that happens here is that all these infinite number of relations, they're just automatically true in my setting. Somehow when I say, so I think I have it just underneath again. When I say my cobordism category is obtained from this one by adjoining these things, then somehow the fact that far away handles commute is built in the fact I'm doing a bicategory in the end. So if in a bicategory, if I have a morphism composed with an identity, and then I compose it in the other direction with an identity composed with another morphism, these two things kind of have a mixed associativity of vertical and horizontal composition. And similarly, the commutation rule for diffeomorphisms and handles can be expressed by the exact same drawing. So somehow, for each, if I fix a cobordism W, then I will need all these relations to relate different handle decompositions. But if I'm interested in the category of cobordisms itself, then I don't need to know about these because just the fact it's a two category will impose these extra relations. So this is the Z, actually symmetric monoidal category obtained from this by joining these and imposing these relations. Okay. Okay, and so here I've given you some notes on how many generators there are. Okay, so does this statement now make sense for everyone? Okay. And so if you're happy with this, I can maybe tell you a little bit about applications of this result. So somehow, okay, how are we going to use this to actually build TQFTs? And so somehow the point here is that it is not too hard to build these series that are only in dimension n+1. So somehow something defined on this part, in many concrete examples, we will understand quite well. And it's really the n+2 dimensional part that's a bit difficult, and so we can kind of now do it a bit more by hand, even if we don't have a very good understanding of the theory. We just need to give an assignment to the handles and check explicitly a bunch of relations. So the example I have in mind comes from skein theory. So skein theory is a theory of some graphs living in 3D. So the example you might know about is this Kaufman bracket skein theory, which tells you something like so you will have graphs in 3D, tangles in 3D, and you mod out by this local relation that every time you see a crossing, you can resolve it in two ways. And this so these graphs in 3D modulo these what we call skein relations that will give you a vector space, and somehow these vector space assemble themselves into well exactly 4D theory, but that's not defined in dimension 4. Okay, so this gives you so to a three manifold M, this gives me some vector space, which we call the skein module of M. Okay, but that's generated by these tangles or graphs in the three manifold modulo some local relations. Okay, and these glues very nicely on surfaces. Okay, so if I have a three manifold that's obtained as a gluing of two parts on the surface, then I can kind of just cut along the surface, and what I will see is some tangle in first three manifold, some other tangle in the second three manifold, and they just agree on the surface boundary. So somehow on the surface, what I need to remember is these points, configurations of points on the surface, where my tangles in each three manifold will, the boundary will be some configuration of point. Um, so actually, when I'm gluing two three manifolds together, I suddenly need these points to like make the boundary match and get a skein, so a graph in the whole three manifold. But to encode relations, I also somehow need a bit more data at the level of the surface. I will then need to do some kind of quotient of so all of these things are also considered modulo isotopy. So somehow I should have some isotopy that pushes things from my first three manifold into my second three manifold through my surface. And so here I also need to remember, so if I have two collections of points on my surface, I need to remember how a graph can link these two things. Maybe do this in blue. So in the end, what I assign to a surface is actually a category, which we call the skein category. That remembers how points can end on the surface and how graphs or skeins can evolve in a thickened surface. This is sigma across an interval. Okay, and so these two things together, they really give me a functor out of cobordism dimension 2 and 3. Okay, and this really wants to be a TQFT. Okay, and it gives me the vector spaces on the three manifold, but somehow I have no good ways of telling you what happens on a four manifold. So yeah, maybe let me write this. So if you have a good way, I'm very interested. Oh, sorry. Messed up. Okay, that. Okay, so I was saying, so we have a very natural thing to do on surfaces and three manifolds, and these glue nicely together into this functor out of this part. But it's very uneasy to describe something on four manifolds. And so there's always a question of, okay, if you've given me somehow the input data you need to give me is what kind of relations, what are the skein relations I'm looking at? And if you've given me this thing, then I'm always interested in knowing, can I do something on four manifolds? And this is not easy to answer a priori. And so this kind of handle attachment approach will tell me that kind of give me a way of doing this systematically. So now I can just define my handle attachments. So I will define some linear maps between these skein modules. Oh, sorry. I will define some maps between these skein modules by hand, and I kind of check these handle relations. And even if I don't have a say complete understanding of the whole story, I will obtain I will be able to like build these once extended TQFTs. Okay. I think I'll stop here for now, and if there's any question, please feel free to ask.
Cool. Thank you, Benjamin. Very nice.
Yes.
Can I ask you a question?
Yeah.
Hi, this is Sean Sui. Can you say a little bit on the so here you said you just need to assign linear maps to the handles of various indices.
Yeah.
So in your paper of constructing this for the TQFT, it seems to me you define like not the linear map, not just associated to a handle, a specific handle, but it's really like let's say you start from a three manifold, right? You attach a let's say a two handle to that, and you get
Great.
a handle of a cobordism from the original three manifold to a new one, and then you define the linear map to that bordism. Well, of course, you
Yeah.
have such a bordism for every possible three manifold, right? You can start any three manifold, and then you glue a two handle.
Yeah.
So it seems like then this way you define a like infinitely many linear maps for
Mhm.
like linear maps for infinitely many cobordisms instead of just a single, let's say, or just a single handle body, single.
Yeah. Yeah. So that's why there's two things here is that okay, so this is probably the paper you're referring to with Costantino here and
Yeah.
Patrick Miron.
Mhm.
Um, and the thing you want is in a paper that I promised myself I would put on the archive tonight. So hopefully
Oh, I see. Okay.
you'll have it tomorrow or the day after that. Um, but so yes, indeed, somehow this is the difference between yes this paper with Costantino, Guy, and Patrick Miron we did using the framework of UHAS. So there you have infinitely many generators and infinitely many relations. Somehow this is exactly because you're not once extended, and so you cannot talk about the handle in itself. The handle in itself is a cobordism with corners, and you can not talk about the Z cancellation of handles because again it involves corners. Um, but so yeah, somehow from this construction, um, with these three people, it is kind of clear. Okay, I mean this is that we could kind of read off what is the map assigned to the Z two handle, let's say, even if you don't close it up into a closed three manifold.
Hmm. I
But
see.
so yeah, you're right. There was something missing here, and it is gonna appear pretty soon.
I see.
Uh,
So you said you just have a new paper today? Uh, just trying to see.
so I didn't
Oh,
post
not
it
today.
yet.
Okay.
So if I post it in the next hour and a half, then it will be tomorrow. If I don't, then it will be Wednesday.
I see. Does this
um,
recover the same result from the CGHP paper?
yeah. It's so somehow yeah. So I didn't talk about it, but since I was even faster than I expected, I could say a few words on this. But then again, motivation for doing these once extended TQFTs in dimension four is looking at some boundary conditions. So maybe you can, if you was down here. Um, so somehow we have this TQFT that gives me okay something on surfaces. So let me call it Z. That it gives me something on surfaces, something on three manifolds. Um, and something on four manifolds. Okay. And so this was some category, this was some vector space, and this was some linear map. Okay, in general, I say vector space, but okay, maybe in general, it's, if M has boundaries, then it should be a functor of some kind, and this should be a natural transformation. Okay. And so a boundary condition um, to the Z will be something that to a surface will assign me a preferred object in this category. so which we sometimes called a distinguished object, something like this. So I have all these categories, which you may think of like how many points in my surface I'm allowing, for example, in my skein picture. And you could say you have a favorite one, which maybe 0 points. Okay. You don't want any points on your surface, and that's the favorite way you would have skeins ending on the surface. And similarly, to a three manifold, you will give me a favorite element. So I could also call it this M. So again, this thing in my picture was some skeins to some graphs living in my three manifold, and I could say I have a favorite one. In my case, my favorite one is again the empty one. There was say a slogan I will attribute to Walker, which is these Witten-Rashtik interior series. From or I don't know, from or come from a boundary condition to some 4D theory. Okay, so for me, this has been one of the big motivation for developing exactly, well, this 4D theory has to be a once extended theory somehow in this setting. Boundary conditions are really defined for once extended series, and this kind of big slogan has been a big push towards developing this once extended 4D series.
So you're trying to make this slogan work in the non-semi-simple setting. Is that correct? Is that maybe?
Yeah, that's also good. Yeah. So somehow this paper is gonna come out tomorrow. Probably is about this part. So somehow you still you do need to worry about a lot about the 4D theory, but somehow what you're interested in is this 3D series that lives at the boundary.
Thank you.
So I'm curious if one tries to like skeletalize the data of one of these TQFTs using this, these handle attachments. Is there a way to achieve that?
There should.
Yeah. I suppose for the surfaces, there's infinitely many different surfaces. One needs something assigned for it. But then modulo that, is there just a finite amount of data that ought to be necessary to get a 4D once extended thing?
Yeah, so maybe the first thing to answer to that is that if you did allow yourself to then also chop surfaces into pieces, and then chop circles into pieces, so if you get a fully extended series, then somehow there is very little data assigned to that. So essentially, you just have to say indeed what you're doing in the lowest dimension you allow, and everything else is already completely determined up to, well, okay, there's tiny bit of choice, but it's very little amount of choice. So in this setting, so a corollary of this result I didn't mention is that if you have two once extended series that agree on the n+1 dimensional path and also agree just on the zero handle, then they agree completely. Somehow these handle constellations, there's only one k+1 handle that will cancel with a given k handle. It's kind of, you have a pairing and there's a unique co-pairing that will. So this kind of idea has been developed a lot by Kevin Walker and David Reiter. And so they have a very similar idea in mind. Actually, they have two peer work that should become very related. But
So
so yeah, if
you need a pair, you need the data of the pairing though, or this co-pairing.
so somehow
Is that what you're saying? Yeah.
so well yeah somehow the only data you need is just one of the handles, and somehow this kind of cancellation will determine the other ones.
Ah,
So
so if
if
you satisfy this cancellation condition and have the zero handle data, then you actually get all the data.
exactly, yeah. So the only data, so okay, there's something in lower dimensions, and if you kind of know already what to do, which for example is our case with skeins, already know what to do in lower dimensions, and you're only interested in the top dimensions, and the only choice you have to make is was the first one, say. I mean, you could start with the last one, you do whatever, but you choose one of the handles. And then it's conditions for the next handle to exist, for there to be some two morphism that will cancel with your already prescribed handle. But if it exists, it will be unique. So um, somehow, yeah.
So, I guess, are you suggesting there's something intermediate between an n+1 plus epsilon theory and an n+1 plus 1? There's maybe n+2 intermediate things in between. Like maybe you get some of the handles up
Yeah,
through some amount, but not the next handles. Is that a sensible thing to do?
that is a very sensible thing. Indeed, that's for example, that's definitely what they do in Walker, what Walker and Reuter do. It's also somehow how the cobordism hypothesis works. If yeah, if you know about that. Interestingly, yeah, well, so there's some annoyance. Say you're working in dimension two, and you know you can do the zero handle, the one handle, and the two handle. But then the three handle, okay, it doesn't work. And fine, you've already defined something on a lot of four manifolds that are obtained out of zero, one, and two handles. But then you have an annoying question: is okay, what are the relations? So sure, you have the zero, one, and the one, two handle cancellations. And now you take two, what they call four-dimensional two-handle bodies, so obtained out of these zero, one, and two handles. Take two of them that are diffeomorphic, then it is open to know if they can be related by just these two handle cancellations. It might be that you need to introduce a three handle at some point, move it around, make it cancel with something else, and your diffeomorphism will not be realized, somehow staying inside things where you only had the handles you authorized. So if you stop partway through it may run into some real difficulty to understand what the relations are.
Would it be
If you
safe to say
yeah
if we went one dimension lower now, looked at 1+1 plus epsilon,
yeah
so when one tries to get the full Reshetik and Turayev 3D TQFT, that's anomalous.
yeah
So is that seen by the two handle or something? Is there in this picture?
so so the anomaly is just gonna mess up with everything a little bit because somehow we should change. Like this category is just not the right category for WRT anymore, even if you disallow some handle.
Okay.
So I would say there's kind of
So
a
not
different
quite.
story of, so yeah, you kind of have to twist these things so that they become the right thing.
Okay.
Somehow still there is some non-summational version of WRT. So this non-summational 3D series. And these are exactly of this type, where, okay, the zero handle works, the one handle works, the two handle works, but the three handle doesn't. You just have no way of defining it. And so they are really this partially defined thing, exactly as you were pointing at. But so you only drop the last one. And somehow this problem I was alluding to, if you really only drop the last one, then it's fine. So these we call non-compact TQFT. I mean, Lewis calls non-compact TQFTs. And they're pretty studied because somehow it relaxes a lot the conditions, so you will have much more TQFTs. And it doesn't mess too much with the topology somehow. This is just Like the last handle is just a closing n+2 ball. It's not that interesting anyways. We're really interested in the handles before that. So it's not a big deal.
So just curious, I don't even know that this is a good question, but with Kovanov homology, could you kind of analyze it with this framework?
Yeah, so there's a lot of work on Kovanov homology. I'm not necessarily fully up to date, but somehow they developed these lasagna skein modules. So Morrison radiation Walker, for example, but many others. And this should somehow fit into exactly this part. So lasagna skein modules, they give you a vector space for manifold, and this vector space looks a lot like it should glue in the exact same ways as skeins glue. So on a 3 manifold, you will kind of look at how your lasagnas or the embedded surfaces may end on your 3 manifold. That's what you will remember, and then you can glue on this thing. So somehow, yeah, it's a very interesting question to ask. Can we extend this to 5D? And then, okay, most probably we can have a 0 handle. I have no idea if we can find a 1 handle, but maybe. And then I would expect it stops very soon. Somehow we already know that there's no way it's going to extend to 5D in the current version. So they have some examples where some graded piece of these vector spaces are infinite. Dimensional. So okay, it will not give us a fully defined 5D series. So I mean, we kind of expect this maybe even from usual skein theory. If you're looking at quantum groups at a generic Q, so you have an infinite. Have infinitely many simple, infinitely many different representations, and you will not have a fully defined 4 TQFT. And you really have to go, say, at a root of unity and look at some smaller thing in order to have a 4D series. So somehow, expectedly, the same thing would happen for Kovanov homology, and we would need this Kovanov homology at roots of unity, which is not, as far as I know, very well understood. Okay, yeah, how does that answer the question?
Yes, yeah. So are there any other questions from the audience? Maybe I'll stop the recording.